All right, welcome back, pre-calculus students, to lesson 2.5 on complex numbers. And so we're going to try to remember a little bit about complex numbers. One of the things we should make sure we remember from the past is that the letter I is equal to the square root of negative 1. That's the notation that we use because we can't take the square root of negative 1. We call that imaginary number. Other thing we might want to, then corollary to this would just be if I squared this, that I squared is negative 1. A complex number would be some A plus BI. Okay? For example, like 1 plus 3I would be a complex number. It's got a real part and an imaginary part. Okay, so that's just a little review again, because this would be complex numbers, a mixture of that real and that imaginary part. So we'll get into that in a little bit. And first, I'm going to talk about factoring a polynomial with real coefficients. So what we know is that every polynomial function with real coefficients, so in other words, we won't have, if I look here, the coefficients here are real numbers, right? Can be written as a product of linear factors. So a linear factor is something like x plus 1 or x minus 3. Those are linear factors. And then it can be written as a product of linear factors and irreducible quadratic factors. So in other words, quadratic equations or expressions that can't be factored anymore. So something like x squared plus 3 can't be broken down anymore, can't be factored anymore. That's an irreducible quadratic factor. All right. So we're going to look at how to factor. We should know how to factor quadratics. We've been doing that for the last couple of years. Factoring cubics, and now we're looking at factoring those quartics and 50s. So how do we factor something that is this incredibly large? Well, what we're going to do is we're going to rely on that last one, the p's over q's. Okay, so that's kind of where we're going to start. All right, so I'm going to look at this equation. I'm going to look at the p's. All right. Again, remember the p's come here from my constant. My q's come from the coefficient of the leading term. So again, now my p is negative 9. So factors of negative 9 are plus or minus 1, plus or minus 3, and plus or minus 9. All right. Factors of q is 3, so that's just plus or minus 1 and plus or minus 3. To get our p's over q's, those I would be able to then now list all of the possible rational roots. All right. I look at finding that ratio. P's over q's. It's 1 over 1, which is just plus or minus 1. 1 over 3, so plus or minus 1/3. 3 over 1, so plus or minus 3. 3 over 3 is 1. We already got that. Then take the 9, so that'd be plus or minus 9. And then plus or minus 9 over 3, which is 3. So just repeated that there. So these are all the possible rational roots. Now, they don't all work. You have to figure out which ones, again, will work. So, what you really should officially do is, look at finding, what's f of 1? Does that, I'm looking to see that it gives me 0. Okay, looking at f of negative 1. What does that give me? F of 1/3. What does that give me? F of negative 1/3. What does that give me? F of 3. F of negative 3. F of 9. And f of negative 9. So I could go through and do all those, put those all back into the original equation and see which one gives me 0. That would be which of the rational roots work. All right. Well, we can kind of fudge this a little bit and have the calculator help us kind of narrow down which ones we can kind of pick. And that's what I've got here. So if we kind of take a peek back at our Desmos, I've already typed that equation in. And we can see the graph. We can see that there are 3 places here where it does cross the x-axis. So I do have 3 real roots. Now there should be 5 total, so there must be 2 imaginary up there somewhere that just don't cross. But now out of the 3 that do cross, are these all rational? And I can see here, -3, 0, that's -1/3, and 3. So kind of just, being honest, knowing what, and being a realist here, figuring this is what you're probably going to do if you have the technology to be able to do it. Otherwise, you'd have to do that all by hand, put those numbers in. But, I'm a realist, so I know what you're going to do. So -3, -1/3, and 3 are the roots, the rational roots for this. So if I go back, again, this -3, so when I put the -3 in, I would have gotten 0 for that. When I put the -1/3 in, I would have gotten 0 for that one. And then when I put 3 in, I would have gotten 0 for that. So those are my rational solutions. Okay, the one here, the one here, and the one here. Okay. So what we do know, if I just start with this first one here, just pick this one. I know 3 is a root. Okay. So what I can do is use some synthetic division to see if I can find some of the other pieces for that. So I'm going to take 3 and take the coefficients of the original function up there, which is 3, 1, -24, -8, -27, -9. Bring that first one down, multiply and add, multiply and add, multiply and add, multiply and add, multiply. And again, you can see again that comes out to be 0. That's what should happen if that was really a root. We should get a remainder of 0. So now what I have, we'll switch the colors now, is I've got f of x equals, and if that was one of my roots, this is the factor. X minus 3 does go into that original equation up there, and we were left with this quotient here, which would be 3x to the 4th plus 10x to the 3rd plus 6x squared plus 10x plus 3. So you can see I'm starting to get this factored up here. But I know there's some other roots. For that matter, I know -3 is a root. So what I know is that -3 should go in, or the factor x would be actually x plus 3 would go into this, or should. So I'm just going to take that root, that -3, and do the synthetic division on this part. All right. So coefficients would be 3, 10, 6, 10, and 3. Bring down that first one, multiply and add, multiply and add, multiply and add, multiply and add. Again, you see you get 0 down there because it should if that was a root. All right. So now I know that with an equation here, that f of x equals, I've got this x minus 3. Now that came from that root up there. So that's the factor for that. This is the root of -3, which is the factor x plus 3. And then I'd be left with that piece, which is now bring down to a degree, so that'd be 3x to the 3rd plus x squared plus 3x plus 1. So you can see I'm slowly factoring that original function. I do also know then that negative 1/3 was a root. All right? So I know that the negative 1/3, so in other words, x plus 1/3 should go into that. So take those coefficients of everything here, 3, 1, 3, and 1. Bring down the first one, multiply, give me negative 1, add, multiply, and add, multiply, and add, and again, should have that, that 0 piece. So now I know that I've got the function f of x equals, and originally now I got that x minus 3, the x plus 3. I'll have this as a root, so that would be x plus 1/3, and then times what I've got remaining here. And that's the 3x squared plus 0x plus 3. Well, I should be able to factor this now with our skills from previous years. Certainly a 3 comes out of each of those. So I've got f of x equals x minus 3, x plus 3, x plus 1/3. Take that 3 out, and I'll be left with x squared plus 3. Conveniently, what I might do is just take this 3 and distribute it to this one just so I can get rid of that fraction. And I'd have f of x equals x minus 3, x plus 3. Distribute that, that'd be 3x plus 1, and then x squared plus 3. Or I'm sorry, if I factor that 3 out back there, ooh, there's a mistake, just caught it. If I factor that 3 out, I've got to factor out of both of those. That would have been x squared plus 1. And same here. And there we go. We've got this factored now down to all of its linear factors. That's a linear, that's a linear, that's a linear, and an irreducible quadratic. In other words, I can't factor that anymore. That does not factor anymore. And you should be able to do that with every polynomial function with real coefficients. You can always do that to factor it down into its linear factors and its irreducible quadratic factors. All right, so there's an example. Let's see if you can do this guided practice number 13 and see how well you do. So we'll pause the video and come back and see it done and double check your work. All right, and we're back. So hopefully, again, you were able to get through this problem and double check your work. So hopefully you got the P's and the Q's first, and then found all the P's over Q's. And then theoretically, you would test each of those 8 terms by putting the possible rational root back into the equation to see which one gave you 0, which ones give you 0. Well, whether you graphed this and kind of looked at the graph to help you narrow it down, whatever the case is, you should find out that it does have an x-intercept at -3. And that would be our only rational root. So we know if the -3 is the root, then the x plus 3 is one of the factors. So we take that -3 and we do the synthetic division into the problem to see what the other factor would be. And should get this. And at that point, again, we've got our linear factor. And here we've got an irreducible quadratic factor. In other words, we can't factor that into rational factors. It's as factored as it's going to get. And there is a way to factor it to get irrational solutions, and you can use the quadratic formula to look for that. But again, we're not factoring that into the irrational parts. We're looking at factoring this into its rational parts. So there's kind of the first part of lesson 2.5. Let's look at the next part. It's called the fundamental theorem of algebra. All right. So the fundamental theorem of algebra says that a polynomial function of degree n has n complex zeros, means real and non-real. In other words, real solutions will intersect the x-axis. Non-real or imaginary solutions do not intercept the x-axis. Okay, and then some of these zeros actually may be repeated, which is again, to remember those are our multiplicities. Multiplicities, get that spelt there. Just as a quick little example, if I had something like f of x equals, say, let's go x squared plus x to the third minus 2, should have a total of 6 zeros. If you include the multiplicities and all the imaginary solutions. Okay. So that's what we're going to look at now, is finding those complex roots as well. So what we just did was just the rational roots, and they worked out real nice. But now we're going to look to see what we can do to find when we have complex roots. So, like for example, if we took the last problem that we just did, all right? We had it. There was our original standard form that we just had from the last problem, and we had factored it down to this. In fact, I think what we did though is that we actually distributed that to each one. So we had that as 3x plus 1. But we had all these other pieces as well too. If we go through and look at the roots that we had here, we certainly had this x plus 1/3, which would have a root of negative 1/3. That's right there. The x minus 3 has a root of 3, which is right there. X plus 3 had a root of negative 3, so that's right there. But these, the x squared plus 1, if we look at this, that's not on the graph. There's no more x-intercepts to look at. Because if we did solve that, if we had this x squared plus 1 and looking for that 0, we'd subtract 1, and then we'd be looking at square rooting both sides, and there we go. There's a square root of negative 1. That's that I piece. And I always remember when we square root both sides in the equation, we always get plus or minus. So this is x equals plus or minus I. So it's telling me there's actually 2 roots here at plus or minus I. Well, how do you graph, an imaginary solution? Well, you don't. Okay, we just know that there's 2 roots, and they both happen to be imaginary. And so that's how we look. There's 2 here, and there's the 1, 2, 3. So we got a total of 5 roots, which we should have. Okay, so just kind of summarizing this information, and this is just there's some following statements about a polynomial function. If k is a complex number. Okay, so in other words, if we have some type of x equals k, like we had up here, we had x equals I plus or minus I. If I had something like that, if I had x equals, let's just make up one here. Let's say I get 3i as a solution. Okay, that this 3i is a 0 of the function. Well, then what I know is that x minus 3i is a factor. Just like we had with other problems. When there were real solutions. If you had x equals 3 as a root, well, then what you had is you had x minus 3 as a factor. So again, that's a root. This is a factor. And if I got an imaginary root, this is what the factor would look like. All right. So let's kind of put that into play with a couple problems over here. And this got to be a little small here, so I'm going to kind of blow that up so we can work these. Got two separate problems here. So what I've got here, it says write the polynomial function in standard form. Okay, right now it's in factored form because I can see the two factors right there. And then we'll look at identifying the zeros of the function and the x-intercepts. So what I got to do here, if I want to write this in standard form, I'm just going to do some foiling. So I'll just have f of x equals, multiply the first, so I get x squared. The last would be plus 3ix. Insides would be minus 3ix. And the last would be a negative 9i squared. If I clean this up a little bit, add the like terms, I get x squared minus 3i, or plus 3ix minus 3x, they cancel each other out. And then I've got minus 9i squared. But again, remember what I talked about at the beginning about this I squared piece. That's I squared is negative 1. So this is f of x equals x squared minus 9 times a negative 1, which would make that plus 9. So this is f of x equals x squared plus 9. So there's our form or equation in standard form. So if we're going to identify the zeros for that, what I got to do is I got to set that equal to 0. So solve, subtract 9 off of both sides, square root. Anytime you square root both sides, you get plus or minus. And then now this is the square root of negative 9. If we break it apart, is really the square root of 9 times the square root of negative 1. Square root of 9 is 3. Square root of negative 1 is I. So we have plus or minus 3i as the zeros. Okay, so those are the zeros. Okay. And then, if we wanted to look for the x-intercepts, we want to look for the x-intercepts. What we do is we put 0 into the equation. But here's the interesting thing here is we're looking at the zeros here. That's where it crosses the x-axis. They're only crossing at an imaginary spot. That can only have at the most 2 zeros. My 2 zeros are both imaginary. So what that means is there is no x-intercepts. No real x-intercepts. All right, let's try another one. So now here we can see that I've got 3 factors. And if I'm going to put this in standard form, we're going to have to multiply these all out. So what I would do is I'm going to multiply those two first, because these right here are what are called complex conjugates. Remember from years past, a conjugate is the same thing, same numbers in the same spots. Like if I had x plus a, its conjugate is x minus a. We call this a complex conjugate because it's a complex number. You've got a real part and you got an imaginary part. So same idea, same numbers in the same spot, one's minus and one's plus. What's kind of cool is I'm going to do that. When I multiply these, again, you could FOIL this and we can look what happened. But if you start to recognize this as a complex conjugate, I'll show you a shortcut. But anyways, let's do the first ones. This would be x squared. The outsides would be plus x root 2i. And actually that I is actually on the outside. It's on the outside, so it's root and the I is on the outside of the radical. So usually I like to put that in front just so you can really see that the I is not underneath that radical. But it's not going to matter in this case here because if I do the insides, then I get minus x root 2i, and these two will eventually just cancel out because it's plus x root 2i and this is minus x root 2i, so it'll cancel out. But I would recommend And when we write these, put that I and write this as I root 2. That way you know for sure that that I is not underneath that radical. Then lastly, if we do the last, minus times the plus is a minus. Root 2 times root 2 is just 2. And then the I times I is I squared. And we can kind of clean this up here a little bit too. So f of x equals, I got the x minus 5. This would be x squared. Again, remember these canceled out. And then here the I squared is negative 1. Negative 1 times negative 2 is a positive 2. So this just would be x squared plus 2. Okay? So, yeah, let's double checking. So that's our factored form still, but we still want to get this in standard form. So now, again, just FOIL again. If I multiply it, I get, first I get x cubed. Outsides would be 2x. Insides here would be minus 5x squared. Last would be minus 10. So I'd be left with f of x equals, put this in descending order, x to the third minus 5x squared plus 2x minus 10. So there's our equation in standard form. All right. If I look at the zeros, again, I think it's always easier if I go back up to the original factored form and set each of these factors equal to 0. So that's that x minus 5 equals 0. So x equals 5 is a 0 or a root. All right. The next one there, I'm setting the x minus root 2I equal to 0. So let's add that to both sides. So that x equals root 2I. Preferably, again, I was saying I like to put that I out front, so I go I root 2. And then the last one there, the x plus root 2I equals 0, and x equals negative root 2I. Again, I like to put that I out front, so we'll go negative I root 2. So those are the 3 zeros, and again, should have at maximum 3 zeros, or 3 roots, or 3 x-intercepts. This one would be imaginary. This one would be imaginary. This is a real one. So the only real x-intercept is at 5, 0. All right. Let's talk a little bit more about some of this complex stuff, and we'll talk a little more about this complex conjugate piece as well. And work some problems with that. All right. So what we're saying down here now for this complex conjugate zeros piece, it says suppose that f of x is a polynomial function with real coefficients. If a and b are real numbers, with b not being 0 and the complex number is a 0 of f of x, then its complex conjugate is also a 0. Really what they're just saying here is that if, and you might notice that up here, that, I got one answer here, the conjugate, or I got one answer here, I got its opposite right there. So in other words, when I got back up here, you noticed that if I have one complex number, I'll have also its conjugate as a factor as well. So, like for example, if I had, if I knew that say negative 6 plus I, that's a 0. That x equals negative 6 plus I was a solution. Okay, I would also know then that the complex conjugate of that, so in other words, same numbers in the same spot, but now we're just subtracting. This too would also be a 0. Okay, so as I go over to a problem here, it says I want to write the polynomial. So in other words, what I've got here is these are some zeros. I've got this one, and this one. And what it's saying is if I have one complex number as a solution, I will also have its conjugate as a solution. So I should also have, if I have this complex solution, I will always have its conjugate as another solution as well. So 1 minus I would be a solution. So if I'm going to write that polynomial minimum degree in standard form that have these zeros, and again, recognizing that I have a complex number as a zero or as a solution, I have to have its conjugate as well as a solution. I've got a total of 4 zeros, so I know I will have a 4th degree polynomial that I'll need to write. And these are the easy ones. To get the factors for these, so I'm just going to say f of x equals x minus 2 and x plus 3. And then this one here, that's one of my roots, so I would have x minus this 1 plus I. You can write those opposites here. And then this one would be x minus that 1 minus I as a solution. And then from here, it's a matter of just doing some of our foiling. And it might get a little complicated in here for you, but we can work out a little process for that. So I'm going to do the easy part first here and just FOIL that. So I'd have x squared. Outside is 3x. Inside is minus 2x, which gives me just an x. And then negative 2 times 3 is negative 6. So that's kind of the easy part to do that one. This one here, again, I will have just multiply some things out here. So you take the first one, so x times x is x squared. Your outsides would be, I got a minus, so minus x times 1 minus I. So again, we're taking the outsides, x times 1 minus I, then take the insides, which would be minus x times 1 plus I. And place that there. And then take the last. So this minus times a minus would be a plus. 1 plus I times 1 minus I. And I'm going to clean some things up a little bit. So let's figure this out. X squared plus x minus 6. Got the x squared here. Really what we can do is kind of multiply this out here so you can see how things will cancel each other out. But you'll have, this will be minus x. And multiply here. And then minus x times a minus I would be a plus xi. Here, you have a minus x. And then distribute there, so it would be a minus xi. And then here we're foiling actually. So first it would be 1 squared, which is 1. Outsides would be negative I. Insides would be positive I. And the last would be minus I squared. Now we should go do a lot more cleaning up here. F of x equals x squared plus x. Oops. Minus 6. And then x squared minus x and minus x is minus 2x. xi minus xi, those cancel each other out. I've got a 1 here. Minus I plus I, those would cancel each other out. And then here, I squared is negative 1. So this is a minus a negative 1, should be plus 1. And another 1 would give me 2. And then from there, we just do our distributions here. Take x squared times each of these, take x times each of those, take negative 6 times each of these. And just to cut to the chase, you can check on this yourself after combining all the like terms. But I'm just going to try to save some time here and say this would come up to be f of x equals x to the fourth minus x to the third minus 6x squared plus 14x minus 12. So just to kind of show that step in between, I'm just trying to cut to the chase to save some time here. But again, you would take x squared times each of those. You'd have x to the fourth. X squared times that would be minus 2x to the third. X squared times the 2 would be plus 2x squared. Do that with each of this. So plus x times x squared is x to the third. X times minus 2x is minus 2x squared. X times 2 is 2x. With the negative 6 here times x squared. Negative 6 times that would be minus 12x. Negative 6 times 2 is negative 12. So when you combine all the like terms here, you'll get this as your final answer. All right. We're going to put it all together here in the last page. So hold on, we'll be right back and move on to that next page. All right, so let's put it all together here and work two more problems. So hang tight here. This one's going to be a little long. So the, oops, where'd it go? There we go. Here, put that a little bit. Question here says, we want to find all the zeros. And again, we're doing this without graphing. And even I'll tell you, from the graphing, you're still not going to be able to find those imaginary ones, those complex roots or those complex zeros. Because you can see here, we've got a complex zero. We're going to have a total of 4 zeros here because of the degree of the polynomial. So we can start off, if we know that 1 minus 2i is a 0, so I know, 1 minus 2i is a 0, so x equals 1 minus 2i is an answer. Well, from the previous page in that theorem, we then also know that its complex conjugate is also a 0. So I know that I will have 1 plus 2i as a 0. So those are the complex conjugates. So what I know then is that x minus this 1 minus 2i and that x minus 1 plus 2i are factors. Again, just like if I knew that, let's say if x equals 3 and x equals negative 3 were roots, I would know that x minus 3, so that opposite one, and x plus 3 are factors. All right? So kind of that same concept. Just got a little more complex numbers here. So if I know that they are factors of each other, what I can do is I could FOIL these. I can multiply these together. So I'll just take this and I'll just rewrite this up here so we can kind of see them next to each other so we can do the FOILing. And we can go ahead and do that. All right. So if I take the first, if I take the first, multiply each other, I'll get x squared. If I take, and this is what's nice about these conjugates here, is when I multiply here, I got the outsides. So I'm going to have this x times this negative 1 plus 2i. Okay, so this is actually a negative x times each of those pieces. So that's negative x times 1, which is negative x. And then negative x times 2i would be negative 2xi. I do these middle ones, again, I got negative x times 1, so that'd be negative x. And then this negative x times a negative 2i would be positive 2xi, sorry. And then multiplying the last, so minus times a minus is a plus. And then 1 minus 2i times 1 plus 2i. If you do that out to the side here, that's another 1 minus 2i times 1 plus 2i. That'd be 1 when I multiply the first. Outsides would be 2i. The insides would be minus 2i. And the last would be minus 2i times 2i, which would be minus 4i squared. I clean this up a little bit. I have x squared. Here I've got minus x and minus x. That'd be minus 2x. So I get rid of those. Here minus 2xi and plus 2xi cancel each other out. Same thing here. The 2i minus 2i cancel each other out. Here 4i squared. This I squared is negative 1. Times negative 4 would be positive 4. Plus that 1 would be 5. So all that work comes down to this. That's these two roots written as factors multiplied give me that. So what I know now is I know this goes into our function. This is where our long division comes in handy, is that this x squared minus 2x plus 5 I know goes into that original 4x to the fourth plus 17x squared plus 14x plus 65. Now what I would do when I do this problem is, again, I'm missing the third power, so I would make sure to squeeze that in. So I'll just kind of rewrite that and have that plus 0x to the third, and then have the 17x squared 14x plus 65. And then we get the fun part of doing our long division. So again, looking at just these first terms. Looking at, what do I multiply x squared to be like 4x to the fourth? Well, that'd be 2x squared. So I'm going to line that up over here. Take this times each of those pieces. So 2x squared times x squared is 2x to the fourth. 2x squared times a minus 2x is a minus 4x to the third. 2x squared times 5 is 10x squared. And then remember to change the signs. And we can add those. So this would be, oops, I'm sorry, I should have multiplied this by 4. Oh man, sorry. I'm not going to go back and re-record this whole video. I should have multiplied by, going back here, you're going to see what do I multiply x squared by to be 4x to the fourth. Oh, dang it, I'm sorry, I apologize. I should have multiplied by 4x squared. So I'm going to take 4x squared times all of this. So 4x to the fourth. 4x squared times minus 2x is minus 8x to the third. 4x squared times 5 is 20x squared. And then we can change the signs. Now that goes away. Here this is 8x to the third minus 3x squared. And bring down the others. 14x plus 65. Then I look at, well, what do I multiply 8x squared to be like 8x to the third? I'll get it right this time. I'm going to multiply by 8x. 8x. 8x times each of these pieces. 8x times x to the third is 8x to the third. 8x times minus 2x is a minus 16x squared. 8x times 5 is a 40x. Remember to change the signs. Add them here. This is 13x squared. And then minus 26x plus 65. Then look to see, well, what do I multiply x squared to be 13x squared? I just multiply it by 13. 13 times x squared is 13x squared. 13 times minus 2x is minus 26x. Look at what's happening. 13 times 5 is 65. And we'll change the signs. And these all fall out, and we end up with zeros all the way across. And that's what we wanted, because we knew that this, when you got this polynomial that I divided into there, it shouldn't have a remainder. So now what do I know? I know that f of x equals, I got this piece, at x squared minus 2x plus 5 times this piece gives me that original equation. It's 4x squared plus 8x plus 13. So I've got quadratics now, factored it into quadratics, and knowing, again, we knew that the roots for this were the 1 minus 2i and the 1 plus 2i. So if I'm looking for the original problem here was asking me to find all the zeros, well, I got that first one was given to me, and the second one is just that conjugate. So if I'm looking down here, I'm just going to write my final answers down here. My zeros, I know one of them is 1 plus 2i. Another one is 1 minus 2i. The other two, because again, remember we get 4 of these because the degree is 4, are going to come from this quadratic. And we can factor that and simply let's review factoring by using the quadratic formula. So we'll go x equals negative b, so negative 8 plus or minus the square root of b squared. So that's 8 squared minus 4 times a, which is 4, times c, which is 13, which is all over 2 times a. So 2 times a 4. So x equals negative 8 plus or minus, inside 8 squared is 64, minus 4 times 16 is 208. Use a calculator real quick on that. 2 times 4 is 8. On the bottom, we got x equals negative 8 plus or minus the square root of negative 144 over 8. And the square root of negative 144, that does come out even. Remember this, you can break that down. 144 as the square root of 144 and the square root of negative 1, so that's 12i. Negative 8 plus or minus 12i all over 8. And we can do a little reducing here. If you look at this part here, that's negative 8 over 8. So x equals negative 1 plus or minus, and we have 12 over 8i. And the 4 goes into both of those, so this would be like 3 halves i. Those are our other two answers. So the roots are, one of those would be negative 1 plus 3 halves I, and the other one would be negative 1 minus 3 halves I. These are all 4 at the zeros. Whew. Deep breath. Good thing you got the video. You can go back and you can slow it down, you can rewind it, take it back and look at it. Let's do one more problem together. And usually I like to have the guided practice be one you try on your own, but I know this is intense stuff. Let's do this one together and let's talk through it. All right. So this question again says, you want to find all the zeros, all right, of this function. Okay. So we're going to look at factoring that. Okay. Right now I know that 3 minus 2i is a 0. Well, bam, right away, what we also know is 3 plus 2i is a 0 as well. Okay. So we've got two of the 4 zeros already for our answer. And I know that, again, because there's the highest degree in this polynomial is 4, there should be a total of 4 solutions. Okay? Mixture of possible real and imaginary. So right now we got 2 of those. We got 2 complex. So what I need to do then is if those are zeros, okay, I then know I've got factors that would be x minus this first one, so minus 3 minus 2i. And I know I've got a factor for this one, and that'd be x minus this 3 plus 2i. Those are our factors. All right. Now, we want to FOIL that out so we can get a polynomial that we know then goes into that. So, we can look at doing our foiling. Now, foiling on this problem. So, I will take the first, so that's x times x, which is x squared. All right. I will take the outsides. So I'll take the x times this minus 3 plus 2i. So really, what I like to do is put that right here in front of that. So I'll say it's a minus x. Maybe what we can do here is we'll do this one step at a time. So this is minus x times that 3 plus 2i. All right. The insides here is this minus x times 3 minus 2i. And then our last is this, it's minus times a minus would be a plus, 3 minus 2i times 3 plus 2i. So we've got a lot of cleaning up to do here. This is just x squared. I'm going to take this minus x times each of those pieces, so that'd be a minus 3x, and then a minus 2ix. Take this minus x times each of those pieces, so that'd be minus 3x. And then minus times minus would be a plus 2ix. So now we've got a little foiling with inside this here again now. So again, we're going to say this is plus. First, 3 times 3 is 9. Outsides, 3 times a positive 2i is 6i. Insides, 3 times minus 2i is minus 6i. And then our last is minus 2i times a positive 2i, which would be a minus 4i squared. Keep cleaning this up. We've got x squared. So we got rid of this one. Minus 3x and minus 3x gives me minus 6x. Those are gone. Here we got minus 2ix and plus 2ix. Those cancel each other out. Here we got 6i and minus 6i. Those cancel each other out. And so here let's get the 9. But I also know this I squared is negative 1. Negative 1 times negative 4 is a positive 4. 4 and 9 is 13. So right now I know this is a factor of this, and it goes into that. Now if it goes into that, what I know is I can divide that. I know that this x squared minus 6x plus 13 goes into my original equation of x to the 4th. We'll make sure we can keep the it's in standard form, 4, 3, 2, 1. Yeah, so there's no missing ones, so I don't have to have a placeholder with the zeros. This is minus 6x to the 3rd plus 11x squared plus 12x minus 26. And here we go. I'll do it right this time. You got to look to see what's leading those first terms. What do I multiply x squared by to get to the x to the 4th? Well, I have to multiply by x squared, so I'm going to line it up over here over the x squared. Now I'll take x squared times each of these. I get x to the 4th. X squared times here, I get minus 6x to the 3rd. X squared times 13 is 13x squared. And remember to change the signs. And you can add. Add those up, that's gone. Okay, this is gone too. Now we've got negative 2x squared. I'm going to bring down the other pieces. Alright, now I'm looking to see what do I multiply x squared by to be negative 2x squared. Well, it's just negative 2. I'm going to line that up over here, just a single term. Multiply by negative 2. Negative 2 times all this would be negative 2x squared. Negative 2 times negative 6 is a positive 12x. Oh, look what's happening. Negative 2 times 13 is negative 26. Change signs, and they'll go away. It should have happened. Again, it should give a remainder of 0 because we determined that was a factor there. So what we have now is, again, we've got that factored. The original problem was factored now into x squared minus 6x plus 13 times this piece, is x squared minus 2. So there's our original polynomial factored. Remember, we can always factor down into linear factors or irreducible quadratics. And our goal here was to find the zeros. Well, we already know those from before. We knew that x equals the 3 minus 2i and the 3 plus 2i that we got earlier. So 3 minus 2i and x equals 3 plus 2i. Those are already two of our zeros. We got those are easy ones. These ones here now, again, I got to solve. And you could solve by quadratic formula, but I think this one is relatively quick if you just set it equal to 0 and 2 to both sides, square root on both sides. Remember, when you square root both sides, you get a plus or a minus. Guess what? Those are our other two roots. Those happen to be just irrational roots, not real numbers. These are complex. So, wow, lots of work, lots of practice. We'll get a couple days of practicing on this. Make sure you ask your questions, and we keep practicing in class.